Hi everybody. In this lesson, we're going to be modeling exponential functions. Okay, so we're going to be creating equations to model some real-world scenarios that would need exponential application. All right, so the first one is the first two are actually they're pretty simple. I'm using them to kind of just show you how we're going to develop this equation. Okay, so. In the first scenario, we have a ball that's dropped. I'm just going to kind of draw a quick little diagram here to help out. Oops, there we go. Here's just a quick diagram. There we go. Okay, so let's say we have a ball up here. All right, so here's my ball, and I drop it. It says it's dropped 14 meters. Okay, so, oh, that pesky 4, I tell you. There we go. So we drop it, it hits the ground, and it's going to bounce. And it says every time it bounces, it's 80% of the previous bounce's height. All right, so, and we want to know what's the approximate height of the ball on the fourth bounce. All right, so let's look at bounce number 1, right? So let's say it bounces up, comes down. What's that height? What's it going to be? So we're going to go, well, what's 14 times 0.8, right? So, you get out your calculator or whatever, and you do that, and you get 11.2 meters, okay? So there's the first bounce, right? All right, let's do, and then it bounces again. It's a little, not quite as high, right? Here's the second bounce. All right, so we're going to take 11.2, the previous bounce height, times it by 0.8, 80%, right? And when we do that, we get 8.96. I've got these written down already. All right, so I don't have to sit here and bore you by pushing buttons on the calculator. Then the third bounce, right? It bounces again. All right, so we're going to take, well, what's 8.96 and times that by 80%, 0.8, and we get 7.168 meters. And then finally, the fourth bounce, right? All right, oops, again, it keeps always making my 4s and the 9s. It drives me up the wall. There we go. Fourth bounce, and we're going to go, what's 7.168 times 0.8, and we do that, we get 3.4 meters. All right, so that's it. So it's basically approximately 5.7 meters is what we end up at. All right. Now, we're repeating something here, right? We're repeating multiplying by 0.8 over and over and over again. It wasn't such a big deal to find the fourth bounce, but what if we wanted to do 10 bounces or 100 bounces or 1,000,000 bounces, right? Then it's a bit of a pain. So there's a repetitive process doing here. But what did we really do? All I did is I took 14, and then I times that by 0.8, and then I times that by 0.8, what I got from that, and then I times that by 0.8, and then I times that by 0.8, right? That's all that really happened here. That's it. If I pulled out my calculator, that's all I did, 14 times 0.8, 4 times. So we can write that in exponential form like this. All right, so 14 times 0.8 to the power of 4. That would be an exponential equation and a quicker way of doing it. All I have to do is go, what's 0.8 to the power of 4, times that by 14, and that would give me the same answer I got before. Now, before I get into the next one and before I get into the equation on your handout, I want to talk about this here, okay? That 0.8 is 80%, right? So this is a decay question. We call this decay, and I got that written up here, decay. Because generally when we're working with percents, what we start at is 100%, right? In this case, we're losing 20% of the bounce height each time. So that's how we got that 80%. Because when we get into the formula, it generally says you start at 100 and you're either adding for growth or subtracting. So it might, instead of saying 80%, it might say, it's losing 20% of its bounce height. So that number in the bracket, that percent in the bracket, that's basically how we calculate that. All right, let's look at another one here. We got a town that has a population of 25,000 people in 2015. All right, so in 2015, there is 25,000 of them. All right, that's what it starts with. Now, it says if the population grows by 7% each year, right? So this is a growth question. So let me just write that down here. When we say growth, right, we've got 100% and it's growing by 7%, right? So that's 107%, right? 1.07. So to find out how many people there's going to be next year, right? It says every year grows by 7%. We're going to times that by 1.07. So I punch that in my calculator, and that means at the start of 2016, they're going to have 26,750 people. That's what we get here. So that's how many people we end up having. Well, we could do that again. Times that by 1.07 to find the amount of people in 2017, right? And if I do that, I end up getting 28,622.5, right? And that's what I got from equals to that, and then so on and so forth. But the idea is, like in the previous one, this is going to be a real pain to get all the way to 2020. It's just going to, why am I going to do this calculation over and over and over again? So what we're really doing is we're taking 25,000 people, right? And we're timesing it by 1.07 5 times, okay? So I'm not going to write out all 5 of them. The idea is, how can we make a formula that mimics this, right? So the pattern is 25,000, right, times 5 1.07. So we can write an exponential form like this. So these are the basics of an exponential formula. And if I do that, that will give me my answer. So let's actually find out what the answer was to that. So get my calculator up. What's 1.07 to the power of 5? And then I'm going to times it by 25,000 people. All right, so we're going to say approximately 35,064 about. That's about what we got. So approximately, what did I say, 35,000? Yeah, and 64 people. All right. So I wanted to walk you through an example of an exponential growth and an exponential decay before we actually get to the formula, and show you how the formula is made. Because an exponential function is you are repeating multiplication, okay? One's growth, one's decay, but that's the key. It's about repeating multiplication. And that's what we use exponents for, right? And that's how an exponential equation is made. Multiplication. I can't talk and write at the same time. There we go. All right, so let's move on to the formula and talk about it. Okay, so this is the formula that basically I just used in those previous 2 equations. It might look different, but it's not. So these are the kind of the starter variables. You can use whatever you want, but notice how we have our y and x again, right? Y and x, and then we got a and b. So now b is our base, right? So b is what we're going to be growing by, right? So in our previous example, that's where b was, we had 80%, right? Or we had 107%, right? So if we're doing growth, we're basically starting at 100% and adding to it. And if we have decay, we're taking 100% and subtracting from it, right? Okay, so again, growth if b is greater than 0, decay if b is less than 0. So if you think back to the previous example, our decay one, we had 80%, so it was 0.8. That was less than 0, right? And the growth one was 1.07. That's greater than 0. Okay. A, that's going to be our starting amount. So if you think back to our previous ones, let me just go back and look at them. A is what's out front. That's this number out front. What did we start with? I started with a height of 14 meters, or I started with 25,000 people, okay? So that's what the A is. That's what we start with. Y is generally our answer. What do we get? So we usually say it's the future amount. How much are we going to have in the future? So what did we end up in the future with the height of the ball? What was the answer we got? Or what did we end up with the future population of the town, okay? The final thing is the x, okay? And the x is how many times are we going to repeat that? So the number of growth or decays, okay? How many periods? How many times is that going to happen? So in our previous example, right, this one happened 4 times, right? 4 bounces. And this one happened 5 times, 5 years, okay? Now, there's a little more to it here where we get into, sometimes it can get a little more technical. So I've broken it down a little more for you, that a lot of times we have to be careful. How much time has passed versus how much time is there in one period? So for example, maybe this thing doubles every 6 days or something, but only 1 day has passed. So like I would have 1 day has passed out of 6. So sometimes we might use a fraction for that. So now the best way to get doing this is let's actually just do some examples, okay? So let's start with some basic ones here. A bacteria culture doubles in size, so that's key. Doubles in size every 3 hours. If the culture starts with 10,000 bacteria, how many are we going to end with? Now, whenever I do these questions, I always like to set things up this way. I always like to list out what is everything. What's Y, what's A, what's B, and what's X. And I would suggest you do that for your homework too. So Y is going to be our future amount. We don't know the answer to that in this question because we're going to find out. A is how much you're starting with. We're starting with 10,000 bacteria. Now B is how much is it growing by or shrinking by, growing or decaying by. Now we're doubling, so you can basically make B 2. But let's think about it in terms of percent. With these doubling questions, B is automatically going to be 2 because it doubles. But think about why is it double? Because you have 100% is the original, right? 100%. Plus, how much did you grow by? Well, if you doubled, you grew by 100%, right? So that would equal 200%, which is going to equal 2, because 200 divided by 100 is 2. So just keep that in mind. The first bunch of questions are just going to be doubling questions. So it's always going to be 2. Or if it says it triples, it's 3, so on and so forth. All right, now, what's x going to be? It says it doubles every 3 hours. So x is going to be, we're going to take the number of hours that have passed. I'm just going to use h for hours, okay? And divide that by 3. So when I set my formula up, it's going to look something like this. For part A, make an equation. So when you're doing your homework, the main thing is to set the equation up. So we're going to go y equals, here's the starter, right? Y equals a times b to the power of x. So y is going to be equal to 10,000 bacteria times 2 to the power of, I'm just going to use h for hours divided by 3. All right, so there's my equation, right? Now, let's do part B. How many bacteria we have in 12 hours? So 10,000 times 2 to the power of 12 hours divided by 3. So remember, how many doubling periods are there going to be? If it's 12 divided by 3, that's 4, right? It's 4 doubling periods, right? So 4 doubling periods. It's going to double 4 times, right? Because it does it every 3 hours. And we're going to have 4 hours, or 12 hours, right? So in other words, it's going to be 10,000 times 2 to the power of 4. All right, and you pull your calculator out and you do that, and you end up with 160,000 bacteria is how much we're going to have. All right, let's do part C. Really the same thing, except how many we have after a full day. So again, y equals 10,000 times 2 to the power of 24 hours divided by 3, right? So how many doubling periods are we going to have? Well, what's 24 divided by 3? That's 8. So we're going to have 8 doubling periods. It's going to double 8 times, right? So 8 doubling periods. All right, so again, you can put that in your calculator. I won't bore you. I got some of these calculated out so you don't have to sit and watch me push all the buttons. And there we go. So when you're doing your homework for these, you don't have to show a million steps. The main thing is I really need you to set up your formula, right? So what's my formula? Like this part right here, right? What's that formula? And I really want you to show me, like over at the side, what's this stuff here? And then after that, you can just punch your numbers in and solve like I did here. So you don't have to do 100 steps and show every single calculation you get. I'm looking for these things. I'm looking for this information. I'm looking for your formula. I'm looking for what you subbed in and then your answer, okay? So those are the key things I'm looking for. All right, let's move on. We're gonna do some more. They're all pretty straightforward, but let's just watch out for some little things. All right, let's get to example 2. Let me just write down here, y equals, right? I want to know these key pieces of information. What is y? What is a? What is b? And what is x? All right, so let's see. The bacteria culture starts with 3,000. So that's my initial amount. That's the a. After 3 hours, we end up with, so that's a key thing. After 3 hours, there's 48,000 bacteria. So that's how much we're ending with. So we basically know the start and end amount. So we're not looking for either of those. We're looking for something else. They want to know, what is the length of the doubling period? Okay, so it's doubling, right? So it's the same thing. B is going to be 2, right? Because once again, it's 200%, 100 plus 100, right? So it's 2. So what we're really looking for here is how many hours have passed, right? Divided by the number of hours, right? Number of hours in the period. And that's what we're really looking for in the period. That's what they want to know. How many hours? What is the length in that doubling period? All right, so let's set this up here. Y equals ab to the power of x. All right, so just to make this a little bit simpler, sorry, let me finish this here. Let's write it underneath here. All right, so we know there's 3 hours. We just don't know the number of hours. So I'm just going to use n this time for the number of hours. That's what we're looking for. How many hours are there in this period? I know there's 3 hours, but how many does it take to double? That's what we're solving for. All right, so here we go. Let's set this up. Let's sub everything in. I got 48,000 equals 3,000 times 2 to the power of 3 divided by n. And you can use whatever letter you want for that, okay? So what are we going to do first? Well, we're going to have to divide both sides by 3,000, right, to eliminate that 3,000 there. Okay, so I do that, and I go, all right, 48 divided by 3,000 is 16 equals 2 times 3 divided by n. Now, we need to solve for n. Now, since I can rewrite, this one we can rewrite. Remember, there's 2 different ways we can solve from a couple weeks ago to solve an exponential equation. One way is, why don't I rewrite 16 as 2 to the power of 4, right? There we go. Therefore, since the bases are the same, remember, we can set the exponents the same. So that means 4 is equal to 3 divided by n. And now I can multiply both sides by n and divide both sides by 4, and n equals 3/4, or 0.75 hours. So that's how many hours it is, right? So the doubling period is 3/4 of an hour. Or we could say 45 minutes, right? Doubling period is 45 minutes, because that's 3/4 of an hour, right? 3/4 of an hour. All right, so there's one where we're solving for something other than the future amount. So that's kind of what I'm getting at. Sometimes you're solving for different pieces of information here. Okay, so we've looked at 2 growth questions. Now we're going to look at a decay question, and this is a really common one. So we got a sodium isotope. It's a science question, right? Has a half-life. So that's the key. Instead of doubling, we're doing a half of 15 hours. How much sodium are we going to have after 15 hours if we started with 5 grams? All right, so y equals a equals b equals and x equals. So y is what we're going to have for our future amount. We don't know. That's what the question's asking for us. How much are we going to have in the future, right? All right, it does tell us we start with 5 grams. Now, a half-life question basically means, think about it. If we do it in percents, you don't need to for this one, because the answer is it's going to be a half. But if you have 100% and then you're going to have half of that, well, you're minusing 50%, right? So half of that, so it's going to be 50%. Well, what's 50% as a decimal, right? It's 0.5. So in other words, half-life questions, you can just automatically make b a half, all right? It's just going to be half. That's what we're repeating, half each time. Now, we got to be careful here. X, it has a half-life of 15 hours. So that means every 15 hours, you're going to have half of what you had. So I'm just going to use h for the hours, or n for the number of hours, whatever you want, divided by 15. All right, so let's set up our equation. Part A. So we have y equals a times b to the power of x. So y equals, we have 5 grams to start with. 0.5 is half of each time. And we're going to take, I'll just use h for hours divided by 15. So how much will we have in 45 hours, right? So that means 45 hours we're going to have 3 half-lives. Why? Well, what's 0.5 times 45 divided by 15, right? 45 divided by 15 is going to give me 3 half-lives, right? So it's going to happen 3 times. All right, so you end up with, what's 5 times 0.5 to the power of 3? Punch that on your calculator and you get 0.625 grams. All right, which is the same as taking 5 and dividing it in half 3 times, right? Now, what if we do it 100 hours in the past? Well, what we're going to do, oh, here's the secret. This doesn't say 100 hours in the future. 100 hours, I almost skimmed over this. 100 hours in the past. So in other words, we're going back. So what we're going to do here is go, all right, we got 0.5, except this is going to be negative 100. So we're saying how much did we have in the past previously, right? So that's not going to divide evenly, so I'm just going to leave it like that. But if I was doing this in my calculator, here's what I do. I just go, I go, what's negative 100 divided by 15? I go 0.5 to the power of that and times it by 5. And you get approximately 508 grams. So that means if we go backwards in time, right, we had about 508 grams in the past, okay? Let's look at one more. Let's look at how much we have in the future again. How much are we going to have in the you're going to have, again, y equals 5 times 0.5 to the what divided by 15. So 5 days, right? Well, 5 days, how many hours? So we're going to times that by 24, right? That's going to be 24. Why did I write 25? 120 hours. Now I'm writing days. Now I'm getting all messed up. There we go. So that's what we're going to use here, 120. So 120 divided by 15, what's 0.5 to the power of that? Times that by 5. And after 5 days, you're going to have 0.0195 grams left. Okay? So this one, why did I want to show you this one? Because again, the half-life thing that we just talked about, right? That's important. And the idea of that in the past, we can actually work backwards. And when we're going back in the past, we're going to make that time a negative value. We're going backwards, okay? All right, let's look at a few more. I started with some doubling and half-life. Let's look at ones that involve percents more now. Okay, we're going to move on and look at some that involve percents more than the half-life and doubling. It says example 1 and 2. I know we already did example 1 and 2. This is coming off basically a handout that was supposed to be kind of the continuation handout. So continuing, but some new examples, looking at percents more. So these are pretty basic examples again. They're usually, none of these are really too hard. It's just sometimes being careful what goes in. Sometimes the X is the trickiest part, or maybe the B, what goes where, right? All right, so let me just set everything up here, get all my A, B, Y, and X set up. All right, so let's see here. House, increasing in value. So the key thing is it's increasing. So we're going up by 2% per year. How much is a house worth? It starts at $200,000, but what's it going to be worth after 17 years? All right, so we're starting, whoops, putting this in the wrong place. A is what we start with. We're starting with $200,000. This is going to be the future amount. That's what we're looking for. That's what the question's asking for. Now, this one's dealing with percents exclusively, right? So we have 100%, it's increasing. So you need to add 2 to that. So everyone, I always say everyone, but if people make a mistake in this, they generally only put the 2 in there. It's 100 plus 2, right? So that's going to be 1.02 is what we're going to use for B. And X, it says per year. So it's not like every 2 years or biannual or semi-annual or anything weird like that. So when we're setting this up, it's basically, okay, the number of years divided by what? Divided by 1, right? It's like 17 years, but there's only 1 year in a period. So it's just going to be 17. Okay? So let's set it up. Y equals AB to the power of X. So Y equals $200,000. That's what the house is worth. And times 1.02. 17 times. So this one's pretty simple compared to some of the other ones. So you punch that on your calculator and round it off. It's money, so always round it to 2 decimal places. $280,048. If we want to get real technical, come on, $48.28. So there you go. Let's check out the next one. Cars, houses might gain value, but cars tend to lose value, right? So you start with a $32,000 car. Almost every car loses value. They're a real money pit, as you'll find as you get older. It loses 15% of your value, right? Well, what's it going to be worth after 78 months? Now, it loses every year, but they're giving us this in months. So this is where we got to be careful. So again, we want to know what's it going to be worth in the future, right? Now, we're starting with a $32,000 car, okay? Now, if it's 32,000 and it's losing 15, B is not going to be 15%. You start at 100. You're always starting at 100, but we're decaying or losing 15%. So that means each year it's worth 85% of the previous amount. So it's 0.85. So that's a big one to watch out for. The number one mistake here is everyone always puts 15 in it. Now the next thing is it's 78 months, but we need that in years, right? So what's 78 divided by 12, right? So if we do that, we're going to get 6.5 years. There we go. Now we can set it up, and the rest is pretty easy. So it's all about that setup. Show me this stuff here like I have set up. Okay. All right. So we got $32,000 car times 85% to the power of 6.5. All right. So you punch that all in your calculator, and that means after 6.5 years, this car would resell for about $11,126.87. All right, so I wanted to do those basic guys, but so I could point out some of this key stuff, right? The idea of subtracting when we're talking about decay from 100, right? And watching out for the units. This is in months, but we're doing it every year. So little things like that, but the things to look out for. All right, I want to do one more example, an important one, and then that's going to be it for this lesson. All right, this last example is kind of a goofy one, but the math is all important. The scenario is kind of silly. We're saying a magic flute has been purchased. I know it's goofy. I think I was bored and couldn't come up with anything. So, but the math is solid and applies to anything. The idea of something gaining value. So a flute's purchased in 2017 for $3. Now, here's where we got to be careful. The value increases biannually by 7%. This is one of those things that drives me nuts. I have to look it up every single time because biannual seems like it should be every 2 years, but it actually means 2 times per year, which drives me nuts because there's not a lot of consistency sometimes in the English language. All right, so 2 times per year. So twice per year goes up by 7%. So let's start by creating an equation to model this, right? Y, A, B, and X. All right, so Y is going to be, what is it going to be worth in the future? Unless we're working backwards and what was it worth in the past? But what's it worth in the future? A is how much does it start? It's worth $3 to start. Now, it's increasing by 7%. So 100% increase by 7%, right? So that's 107. And when we put it into our formula, we always write as a decimal 1.07. Now, here's where we got to be careful. we're not going to divide this time because it's twice per year. We're actually going to take the number of years, right? 2 times the number of years. So whatever those years are, right? So 2 times the number of years. I'm just going to use n for the number of years, okay? 2 times n. So for part A, here's my formula, right? Y equals, well, let's write the basic out there and then I'll fill it in. Y equals 3 times 1.07 to the power of 2n, where n represents the number of years and y represents the future amount. Okay, so let's solve some of these things. So let's do part B first of all. What's it going to be worth in the year 2058? Well, we got to figure out how many years have passed. So what's 2058 minus 2017, and we end up with 41 years. So what's it going to be worth in 41 years? We sub that into n, right? So what's 1.07? 3 times 1.07, 2 times 41, right? So 2 times 41 is going to be 82. So you go, all right, well, what's 1.07 times to the power of 82 times 3? And it's going to be worth $770.18 if it keeps growing at that rate. All right, so there's that part. Part C, I'm going to skip part C right now. Not that it's not important. It's just not really needed right now. It says determine the increase in value in the 10th and 11th year. So all we're going to do is, what you'd do is you'd literally sub 10 in, and then you do it separately and sub 11 in for n, like you'd replace n with 10, and then you do it another time, sub n in with 11, and then you'd find out what is it worth in year 10, what is it worth in year 11, and then just subtract the two. I'm not really interested in that right now. I want to get to D. That's the one I'm really interested in right now. So part D, what year will it be worth $2,603.15? So let me set this up again. So what we're basically doing here is we are going to set y equal to that amount, right? The future amount. And instead of solving for y, we need to solve for n and figure out how many years have passed. All right, so let's do that. So I have 2603.15 equals, so I'm just replacing the y here, equals, or here I guess, equals 3 times 1.07, 2 to the n. All right, so what do we got to do first? Well, first we got to divide both sides by 3 to eliminate that. And when I do that, I kind of get an ugly number. You can just leave it like that for now, but I'll figure it's 867.716 repeating equals 1.07 to the 2n. Now, what do we do now to solve for n? I can't use that trick where I make the two bases the same like I did a couple questions ago. Do you remember the secret I taught you a little while ago? Using the logarithm. You have to take the log of both sides, right? So what does that allow us to do? Well, let's take the log of both sides here. 867. Now you could have used the log on that other question. It was just a lot easier to write the bases the same. Remember, it allows us to drop the exponent down. Here we go. And now everything's in the same line, right? So now I can divide both sides by the log of the other side there, which is 1.07. So it's a lot of calculator button pushing here, right? All right, so you're gonna have to do the log of the top divided by the log of the bottom. Punch that on your calculator. See if you can get the same answer as me. And if you do, you basically get 100 out. It's a little bit off, but it's basically 100. And then I'm gonna divide both sides by 2. There we go. So we get 50 years, right? So our answer is it's 50 years in the future. Well, it does say what year. So all we got to do is go, all right, well, what's 2017? That was when it started, right? Plus 50 years. So it's going to be right around the year 2067. And there's our final answer. All right, so I wanted to do that example because in that case, again, there's 2 examples I've done with you now where we're solving for the exponent. In one case, we could make the bases the same. Remember, it was like 16 equals 2 to the something. I don't remember what it was. And we could rewrite that as 2 to the 4, right? That works great if you can make the base the same. In this case, I can't rewrite that to be the same as that. It's a mess. So if you have decimals, ugly numbers, which is more common than getting a scenario like this, that's when we use the log. And we take the log of both sides, which allows us to drop that exponent down. And then we can isolate the n and solve. All right, so that's the end of that lesson. Try those questions, and don't be afraid to ask lots of questions about these. I'm happy to help you out on them.